what I want to go through this talk with is essentially give you some history and some evolution of the file systems, and have from that get you an understanding of the overall view of the file systems, essentially how the file systems live within NT. Throughout the talk, pretty much the talk is going to be based upon broad strokes. I'm going to try to avoid going into minute detail, leaving the minute detail for people to talk later. So what I'm going to do is I'll just try to show you the environment and the structure that the file system lives in. I'll try to spend some time throughout the talk explaining to you what is really mandatory of any NT file system and what's optional. Actually, before I go on, I should say, when I say file system, for me, I'm sort of a biased view. I mean more of a traditional file system where you have the data stored on the disk and you have a file structure on top of it, and you have users essentially reading, writing data, creating files, and deleting files. As opposed to more modern file systems or up-to-date file systems which might go off on the network or do some other weird things. So my bias is a very traditional file system. That's pretty much the level of the talk I'm going to go through. Let's see. So essentially the outline I want to do is essentially, I can drop something? No, it's okay. I want to spend the talk telling you about how everything starts in the file system. Essentially, we'll tell you a little bit how we get loaded by the file system, how the file system gets loaded, how it mounts the disks, and then how it starts running, reading, writing, creating files. After you get a big overview from that, I'd like to spend some time on the basic programming environment that the file system lives in. Which operations are available to the file system, sort of who calls the file system, who the file system can call. Essentially, it's the environment that it lives in. At the same time, then I'll go right after that, I'll talk about the data structures involved. Essentially, for the file systems that we built, the data structures we found convenient to use in doing the file system. And then I'll go through, at least at the major IRP level, the major function level, all the IRPs processed by our file systems. And it'll be a fairly quick summary, but I'll try to go through and tell you which each one does. And at the same time, tell you what's required and what's not required. Let's see. Beyond that, we're going to go then sort of go into some other stuff. I'll spend some time talking about how fast I/O works. Fast I/O being just a faster way of doing I/O than using the regular IRPs. I'll talk a little bit about posting I/O requests. I looked at Daryl's slides. I guess he mentioned that a little bit. I'll spend some time about how we handle page faults in the file system, some error handling, and give you an overview of a skeleton structure that we use. Okay. Okay. Actually, that's right. I'm trying to figure out where I am. I'm sorry. Okay. The way the system gets started from a file system viewpoint is the file system, one of the parts of the file system, it has to load itself. And it's in the driver initialization phase of the file system. When it does that initialization, it actually will put itself in a list of file systems that will be recognized by the system. And then the system's job is, where really the IO system will go through when it wants to mount a volume, it'll actually just go through this list trying to find a file system that'll accept the volume. In the particular example here, I have NTFS, HPFS, FAT, and RAW, and then we're all done. If RAW doesn't take the volume, no one will in this case. Okay. So what happens is the way it works is there's a recognizer. I don't know if Daryl talked about the recognizer, but there's a file system recognizer for our traditional file systems that will see if the file system has to get loaded. Once the file system, if it has to load the file system, they'll load the file system in, and once the file system gets loaded, it puts itself in and it registers itself as a file system in the system. Okay. Yes. Then what happens is the system would have, if a user is doing an open file, it'll translate off into a mount request eventually. Say it goes off to a device object that's not mounted by the system. We get a mount request coming in. And the way the mount requests go in, I don't like that slide. The way the mount requests go in, that way. That's the same slide. The way the mount request goes in is that we get an IRP that says, I want to mount a volume in the file system. And the IRP, what it contains is it contains a pointer to the file system device object that was created when we initialized the driver itself. So we are a file system in the system now, and we created this file system device object. We also get a pointer to the volume parameter block, and we also get a pointer to the device object that we talk to. We call it our target device object. Okay. These fields actually aren't put in at all when we get the mount request. So in fact, this field is actually null off volume parameter block. So we get a mount request coming in, and the first thing the file system has to do is it actually creates these fields using we call it the volume device object, and we happen our file systems put some control structure right underneath it that gets us all around the place. And later on, when I talk about our internal data structures, we'll see this one pop up quite a bit. So once this structure is laid out by the file system, it essentially can send requests down to its target device object or the real device underneath it, which is essentially goes off to disk, asking it to read part of the disk. So, for example, in the case of FAT or NTFS here, it doesn't matter. When we want to do the mount, we set the structure up, and the second thing it does, then it starts sending off requests to read, for example, the first sector of the disk. It reads the first sector of the disk, brings it in, sees if it recognizes it as NTFS, HPFS, or FAT, in our case NTFS. If it doesn't recognize it as NTFS, for example, it has the wrong bits sitting out there, then its job is to tear apart all of that structure again, null out this field, then go back to the I/O system and say, nope, not me. And then the I/O system will go off to the next file system and ask it the next one in order. Okay. If it does recognize it, then the file system has to go through, build up all of its data structures to process the mount request. For example, it might want to find out how much is free on the disk, so it might scan all of the bitmaps, or in case of FAT, all of that to find out what's free. It might want to read in the root directory of the disk. It might want to perform some checksum, and it might want to do some restart if you have restart on the disk in NTFS's case. Once that's done, we can complete the IO request packet for the mount saying the mount is complete. I should tell you, there's a mounted bit in the volume parameter block that the file system isn't, I hope I'm right. If I'm not right, I'm sure David Goebel will correct me tomorrow. The file system isn't allowed to set. Okay, I should tell you, if you're doing a file system and you decide to set that, you're going to crash your system. Because what that does essentially, I believe, is it stops other open requests from coming in until we're done processing mount. Okay. So all the file system has to do is set the pointers up and then complete the request saying it's my system. Okay. Once that's established, all opens or creates, reads, write, closes, file system controls, volume controls, device controls will go straight to the file system that mounted it. Oh, I see how that works. Okay. And essentially that's what I just said here, which is once we're mounted, the file system just simply owns volume. And it keeps on processing operations until the shutdown occurs. And when it gets a shutdown, the IO request packet has a shutdown, cleans up all of its structures, flushes all of its data. Can this one go off? I'm getting some feedback. Cleans up all of its data structures if necessary, and completes, and the system's down. Okay. Okay, so that's how we mount the system. Now I'll give you a little idea of the basic programming environment that we use. I don't get tied up in a knot. Okay. I like to think of that file systems themselves live a very sheltered and privileged life, like the developers. It's sheltered in the sense that the only person who'll ever send us a request is really the I/O system, and it's well formed, the request it sends us. Okay. And we're only allowed to talk to a few different people. We can't go talk to everyone. So we're really sheltered in that sense. But we're really privileged in the sense that we run in the kernel and we can crash the system at any time we want. We can take up all of memory. We can just take up all of CPU. We can do whatever we want. Divide by 0 if we like. Okay, so we have to be very careful with where we live in the file systems. Okay. Basically, the file system, like I say, most of its requests, or all of its requests, get sent down by the I/O system using either I/O request packets or using callbacks that the file system can establish. That I'll talk about a little later. Okay. So that's how the requests come in. The file system essentially decodes the I/O request packet, figures out what it wants to do, and at its disposal we have a bunch of file system runtime libraries. The history behind it is sort of mixed. What it was is that historically when we did one file system, the original FAT file system, we didn't have a file system runtime libraries, we only had one file system. And when we started adding HPFS and NTFS to the mix, we started saying, gee, there's a lot of code in common here. So things slowly migrated out to our file system runtime. When you look at it, some of it, you'll find that it's really tailored for the type of file system development we did, for the actual file systems we have. Okay. I believe tomorrow we're going to be talking about the file lock package that's in there, along with the op lock package, and some of the packages that are in here that are really important for you to use if you want to be a file system. And so we'll cover that tomorrow. Other things the file system can do, it also calls the cache manager through procedure calls, and memory management indirectly through the cache manager. What that is for essentially the file systems that we have use the cache manager to maintain all of the caching it uses. In other words, some file systems you might think of would be ones, the older ones or more traditional ones would allocate memory on the side for its own buffering, probably on a non-page pool, and just simply use that for its own caching. Within NT, we did a little bit differently. Now, the bad point about that first one, or the good points about it, is it's really easy to implement, and you can probably get really fast caching with it. The bad point with it is it's not very dynamic. It can't grow with the demands on the system, or shrink with the demands on the system. So what we did is, in NT, we explicitly put in the fact that the cache manager that we use is sort of in bed with memory management, where if memory is really tight on the system, it's memory management's responsibility to get rid of dirty pages to start freeing up memory. If memory isn't tight on the system, the memory management was supposed to let us grow and use up quite a bit of memory. And so that's the procedural interface we use with that one. And then actually the next talk, when Tom Miller comes and talks, he'll describe this interface for you. And this is how we do the mapping. The other set of procedures we have available are, I like to call these the executive support routines. These are routines that allow us to do synchronization of the system, such as we have an executive resource package that allows us shared or exclusive access to the system, different resources that you like. There's the spin locks and the mutexes that we have in there just for synchronizations. There's some other things we have in there so we don't get interrupted and stuff while we're running that we use. And lastly, the last person we really talk to is the disk driver itself. And some people might, it could be the mini port driver underneath it, but from the file system's viewpoint, it's just a disk. It's just a disk that would simply take read and write I/O request packets for reading sectors or reading or writing sectors on medium. Okay. So that's, in a very broad stroke nutshell, what the programming environment looks like that we use. Let's see, what time is it? I believe I already said that. Yes. That's essentially the list I went through. Okay. All file systems would live in that little programming environment that I mentioned. Okay. Any particular file system you write or we write or anyone else writes can have different data structures involved that they want underneath it. What I'm going to do is essentially describe to you what we use in our file systems here, just to give you a probably as an example of what's good for you to use or what we found out works. Okay. I should say in this case, a lot of it you're free to roll your own data structures. Okay. But this is what we have found useful in ours. The structures we have in memory, the data structures we have in memory, how they're set up, we essentially use it to mimic the open volume structures on the disk. So we would have, I called it a volume control block really quickly. We have one little block that essentially says this is a volume on the disk. All right, this is a partition that we have mounted. And for every partition mounted in FAD or NTFS or HPFS, we have a volume control block. The volume control block essentially says the size of the disk, how much is free on the disk, its label. It also contains the resources that's used for locking that volume. So if you want to open up the volume DASD for exclusive access, we would have a resource there that you would grab exclusive access for. And if you get the exclusive access, then no one else can grab it. Okay. We also have two other structures that essentially mimic our volume open structures. We have directory control blocks. They just denote open directories. They actually open directories in two senses. It could be the directory that you've opened directly. For example, you might have gone from /NT/system32/NTOS/kernel.exe and opened that, in which case we'd have a directory control block for system32. But we'll also, in the meantime, open up a directory control block for all the intervening directories, such as /NT would have a directory control block. And the other structure we have is we have a file control block, which for every file itself that you open up, we create the file control block. The file control block tells us the size of the file, where it's located on the disk, the dates on the file, along those lines. It also has the synchronization information stored there. And actually the structure that we have here. So this is the example where you have multiple volumes laid out. Each one, we sort of, since the real way it goes is that since most of the directories that we deal with, directory structures, the traditional ones, are trees, or in some sense, if you allow hard links, could be DAGs, directory acyclic graphs. They all start from one little root directory. So the ones we have is we have the volume control block, has a pointer to the root directory itself, and the root directory can have off of it, in a nice tree form, it can have open files that you would have, and this doesn't show it, but you can have another directory underneath it with open files underneath that. So essentially, if you look at the file system sources, even also CDFS, you'll find that there's this directory structure that's opened up that we use, just to mimic open file structures. Okay. Now what we do is, given that you have this structure here that mimics the file structure on disk, we have to tie it into the actual I/O system or to the actual T system when a user wants to make a request. We do that using the file objects. The file objects themselves are just, they're from the file system's viewpoint, they're just some object that the user uses to identify an open file or open directory. And we use it as a hook back to our system, back into our own data structures. So if you were to think about it, the way I like to think about it is this structure here, including this one really, sort of on the side, is all the file system's data structures. This is everything we as a file system own and can manipulate and use. This file object up here is just the moniker that the other parts of the system use to get into us. Okay. Now, on a create call, what will happen is you will get a file object brought in, or an open file call, you'll get a file object brought in, and the file system's job, or the file system's work function, is create the data structures associated with the file, and then set up pointers into it, back from it, because that's what it's going to use coming back. What we have is there's actually in the file object, you'll find that there's two fields that we can use. One's called fscontext, the other's called fscontext2. And we happen to use them for 2 pointers. The first pointer points back there to the file control block, which in our file system cases is always preceded, or the first part of it's what we call the FSRTL common header. I'll describe that in a little bit while. The second one, we have our context control block, which is for every instance of that open file, we have a different data structure. We have a structure set aside for it. That'll contain, I think it actually used to contain like the file offset, where you were in the file. So if you're doing reads or writes. I don't believe it's there anymore. I think it actually got moved. But I know, for example, when you're doing, if this is a directory, and you're doing directory enumeration, then we would store the context where you are in your directory enumeration. Okay. So what happens for every file object has its own CCB, and you can actually have it here. This doesn't show it, but I'm glad when you made multiple slides for me. Thank you. We would quite often have multiple file objects pointing off to the same file header that's there, same FC. Each one of them would have a different CCB. Okay. And this would be a case where the user just did multiple opens, or multiple users did multiple opens on the same file. Okay. One thing I should say, it's up here. What keeps the file object around once it's open is what we have. We have a reference count and a handle count. And I can tell you the way it works is that when a user does an open on a file, they get a handle to a file object. A file object gets created. It gets a handle count. So the handle count is how many handles the user has open to a file, on a particular file object. If you duplicate the handle, you duplicate the handle count because it's pointing off, it's referencing the same file object. Okay. So that's how often the user has it open, the handle count. The reference count is how often anyone has that object referenced. Each handle count counts as one reference, but inside of the kernel itself or inside the exec, you can actually reference the file object as many times as you want. And essentially, you want to reference it to keep it from going away. It's just you can do the reference the file object by handle or by name or by object, I believe, and just bump the reference count. By bumping the reference count, meaning we won't get a close on that file. So if you want to keep it around, you can just bump it. Okay. Let's see. What about streams? Where do streams fit in? Where do streams fit in? Streams fit in. The question is, where do streams fit in? I wasn't going to take questions, but I'll take them anyway, because I'm going far. That's fine. And that's actually a very good question. The way we have it, you're talking about an NTFS where streams fit into the NTFS. That's a good question. If I were to redo the data structure, I'll tell you the real truth now. Okay. We would have up on top this VCB sitting there. And underneath it, we would have the DCB and some FCBs maybe laying around. What we have is for every FCB, we would have multiple streams. And these are what we call SCBs, stream control blocks. Okay. The way, some historical perspective, then you'll probably understand a little better. I don't draw the picture right. This was the data structure we used when we did FAT, NHPFS. Okay. We did the VCB, the DCB, and the FCB. Well, it turned out that, it just didn't turn out. The FCB we decided to make in page pool, just because page pool is a little cheaper for us. We wanted to use as much as we can of it. And we had what we call the non-paged FCB, put in non-page pool, where the non-paged FCB essentially contained all the kernel all the important information that had to stay in non-page pool for that stream or for the file. Okay. With NTFS, when we started allowing multiple streams per file, we quickly hand-waved, changed the name from non-paged FCB to SCBs, and allowed you to have multiple SCBs there, where each SCB there represents a different stream on the file. Okay. So what happens is you could have the user might do an open, say, of just the regular data stream of a file. You'll have a file object sitting here that references this guy. He might do another open to some other named, maybe a named data stream on file, in which case you'll get another file object referencing this guy. Okay, so we'd actually have, in this sense, we have the tree blowing out a little bit more from DCBs to single FCB. From the FCB, we'd have multiple SCBs. And after a while, you get tongue-tied. Extended attributes? In NTFS, we do extended attribute as an SCB. It's actually a string, if I remember right. I might get corrected. I can see someone back there who can correct me if I'm wrong. But I believe we do extended attributes as a single SCB stream. Okay. Okay. Can I go on? Where am I? So let's see, where am I now? No, yes, this is pretty much what I was going through. I'm saying the handles are the mechanisms that the user uses for accessing a file. And the way it would work is that the user has a handle, it goes and makes a call, like an NT read file. The handle gets translated to an object, and then the file object is what the I/O system puts together and sends it back down to the file system. Okay. And it's handles and reference counts keep the files from going away. Which is sort of, actually the reference counts is sort of a good and bad thing I should warn you about. Is that you can always reference an object to keep it from going away if you don't want it to go away right then and there. But you better be darn well certain to dereference it when you're done, otherwise you'll probably leak pool after a while. Or you'll keep your files open longer than you want. Okay, so you can run into a lot of trouble that way. So that's some bookkeeping that you have to be very careful about maintaining, is your reference counts. Okay. One thing you'll find that when you're debugging, just to give you a little sort of gotchas that we wound up a lot of times, is that if you don't reference it, and you forget to do a reference your file object, or any object, and you start playing with it, it can go away on you at any time between any two instructions. And trying to debug that's always a big pain. Okay, so that's just sort of a warning when you're doing a file system. You really want to make sure your reference counts are right to keep stuff from going away. And I'll just try to push this one up. Okay. And like I said, the context control block is on a per open file system information about that file object. Okay. Let's see. Now I get to a fairly long list here. This is, as of hopefully a week ago, a very complete list of all of the major IRP functions that process in the file system. Some of them are mandatory, some of them aren't. And I'll try to go through which ones aren't and try to explain to you what each one does as we go on. This is sort of just the list. You'll find some of them, the division of the major functions and then later the minor functions is more for historical reasons than anything. It was just an evolutionary process within NT. You'll find that, for example, the cleanup and close are fairly obvious. They only do one little thing to their file objects. Same with flush buffers. Then you'll find out stuff like the file system control or the other control functions that we have that really are fairly complicated in what they do and take a lot of different operations. Anyway, well, I'll just go through because the next slides have them laid out. Okay. Now, why does it say must or should? put it this way. If you're doing a file system, you better do this, otherwise you'll be in trouble. Okay. The order, I believe it's in alphabetical, but that's okay. I'll start here down here because this is the first one on this line you really go through. The create operation is used whenever a user wants to open or create a new file, or open or create a directory, or open a new volume. So when you actually do the create, you have to process it as either a file open, a directory open, or a volume open. And there's one little side one that's not on this slide. I'll mention it, but I don't want to go into detail later if you want. There's some special opens that go on when you want to do a file rename. It has to do with opening what we call the target directory for the file. So you don't actually open the file, but you might open the directory that it's in, and things like that. But that's essentially the operation of create. Well, for us, you can think of what the create does is it generates, like I said, the directory, the DCB and the FCB and the SCB structures that we have. So that's what generates the structures. Okay. Once the user is all done with the file, the user would close the handles to the file, and when the last handle goes away, then the file system gets a cleanup call. Essentially what the file system knows then is that the user is done with the file. The user is not going to modify the file anymore. There isn't going to be more writes to the file or reads from the file. So the user can clean up a lot of that structures that are used. It doesn't mean we're all done with the file. There could still be actually writes going to the file. For an example would be if it was being cached data and the memory management just hasn't cleaned up all of the data structure, all the memory part, all the pages for the file, the user would do a close, and it's only after memory management does all of its cleaning up and all of its flushes of data, or the cache manager, they would get the close. The close is posted by the I/O system when the file object is ready to go away. Essentially, the file system is the last person to touch that file object right before the close occurs. Because right when we return from the close, the object goes away, and it can't be referenced anymore or used anymore. Okay, those are those operations. The other operations we have is we have device control. That's really the easiest one for the file systems to handle. That essentially says, here's a control function that the file system really has nothing to know about. It just wants to send it off, pass it on to the next layer of device in the low-level device, this target device object. Device controls are, for example, locking the media, unlocking the media, ejecting, stuff like that. Or I believe like doing a low-level format call would be down to that using those operations. So those just pretty much just pass through the file system. Again, I think that should be gone. If you want to do a file system, you really have to do these. Okay. We have directory control functions where the file system, the directory control is used to query the contents of a directory. You can return the basic information for every file that's in that directory. And the operations you have to be able to perform on that is to query. You might want to return just one entry. You might want to return multiple entries up until the user's buffer is filled up, and things like that. Okay. The file system has to keep context around, so on multiple calls to the directory control, the directory query, it knows where to pick up where it left off last, and that's what we use the CCB for. The file system control is actually the catch-all. The file system control major function has a lot of different minor functions that we process. Actually, I don't know. I take that back. They're not the minor functions. They're actually in the ERP stack locations, if I remember right. Different controls. These would be used for, the file system control is used for mounting the volume, for unmounting the volume, and there's a bunch more. I can't remember off the top of my head. But it's sort of the catch-all that keeps on growing on us. The flush buffers call is essentially used by the I/O system or the user to flush all the user's data to the disk, all the cached user's data. After it returns, we really want all the data to be flushed, so it should be a synchronous call. It's some ways up to how you want to do your file system, whether you want it to also flush all of the ancillary data structures for file. Whether you want, it's probably a good idea to flush all the retrieval point information, the file size, but I believe that's actually optional for the file system. It might mean when you crash it'll be inconsistent, but that's your file system. Okay. Then we have a few other major I/O control calls. We have the lock control. Give you an idea, the way the file locks work in the system is that when the file system gets a lock control, the lock control is essentially for byte range locking on a file. You can lock any range of bytes you want on a file for exclusive access, for shared access. So essentially you want to lock it so no one can read from it or no one can write to it. Or essentially that's what you're doing. And the lock control essentially say I want to lock this range or I want to unlock this range. And there's actually some more parameters that go on there. You can unlock all the ranges opened by this file object. You can unlock all the ranges based upon a certain key for a file object. And we'll go more to that tomorrow when we talk about because we actually process these in the FSRTL package. That was one thing we did. So as far as the file system proper itself is concerned, it just shuffles those off to the FSRTL and says, you do the work for me. Okay. The query EA major function is also just to return the EA information, the EA string about the file. That's really a holdout from, is it a holdout from OS2? I think it's a holdout from OS2 age. Okay. And we have some more functions here. I just want to sort of give it a flavor of what each one does. The query, the file information, returns like specific information of file. It returns the basic or the standard information of file, which would be the file size, its creation date, its allocation size, its attributes, that information. We also query the volume information. So you can get the volume label, whether you support NIST case, whether the directories are actually sorted by an ascending or descending order. I can't remember which one it does it now. I think it's ascending order. Or it's graphically sorted. And then we have, so that's information. Other three ones we have down here, reading. That's a basic, just reading the data of a file. So once you have a file open, you can read the data from it. So we get the IRP for the read. For the read, we actually will have in it where you want to read it in the file and how much you want to read. The set EA is just the opposite of the query EA. Then we have the set information. EA? Like I said, I think it's a holdover from OS2 that we unfortunately had to carry along. Extended attributes. You only need it if you want to be OS2 compatible, I believe. If you don't want to be OS2 compatible, you can forget it. I believe that's true. What extended attributes are is they allow essentially they're just named attributes. You can say, here's the name of an attribute and here's some data for it. And it's just a way of packing all that into one big stream, the way EAs work. And so you can say, oh, I want to find out what you can have, say, what's the icon for this file? So you have an icon name and you want to have the data for the icon following it. It was all packed in. It's rather limited because the space for it, definition for it was, I believe it was all 16-bit oriented. So the usefulness of the EAs is actually marginal at best right now. But we keep it there for historical reasons. And we have set file information where you can set the date of a file. I believe you can set the dates on a file. You can set the attributes on a file. You could redo the file size there, and that's actually how you delete the files. Slight little sidetrack. I can tell you the way you delete a file in NT is a little different than you might do in other systems. The way you delete a file in NT is you open the file, and I believe you need delete access. You have to ask for delete access. Then you mark it for delete, and then you close the file. There isn't a single delete file call, so it's a three-step operation for us. We used to, in fact, allow you to open the file, mark it for delete, do some work on the file, decide after a while you really didn't want to delete the file and undelete it, and go on, but I believe they removed that capability. For the file systems, for our file systems, it's when the close would occur. So when the last, it's not when the cleanup goes, but when the close occurs, then we know to go through and actually delete the file on the disk.
What exactly does that entail?
For example, in the terms of, an easy one would be like for FAT. If we do a delete on FAT, that's this example. You just have to go to the directory entry for FAT, put the little deleted byte in the front of the directory entry, flush that out to disk, and also go to the FAT table itself, which has all the retrieval, and just zero out all your retrieval information. For NTFS, it's just as simple. We have to do some deallocation of your file record, and remove yourself from the actual index or the directory that you're in. Quick question?
Previous call to create, there attributes set that you know the call is going to come through after the delete.
Sorry, I missed the question.
Okay, when you're going to delete a file on a key, and you get a create for the file first, are there attributes that call that create so that you know the only call that's going to come through is delete?
Gary, can you repeat the question?
I'm trying to understand the question.
I know.
I guess the question I have is on a network file system. You get a create, and the operation that they want to do on it is delete, so that you don't send the packet out on the network to the open. How do you know what the only operation to come down is the delete after they open the file?
You don't. I think that's the answer. You don't focus on the operation.
So you have to honor the create.
Yes. Yes.
What was the discussion? Sorry.
The question was, I guess if I can condense it, would be, if you did a create, could you know that the only operation you'll ever do after that is a delete then a close? Is that the way of phrasing it? And the answer is no. There isn't any way you can do it, because once you did the open, you're free to query it, you're free to do any queries you want on the file. You may not have open for read or write access, which would be okay, but you're still free to query the external attributes of it, and find or the attributes of the file. Pardon me?
You do a create with delete on close, but other people can still do a create without any of those flags. Still get to it, correct? User one doesn't create with delete on close. You can still have multiple people just doing create on that same file.
I believe so.
As soon as they close all the handles, it does.
Let me continue on and take more questions as I get closer to the end. I'll take more questions when I go on. Okay. So these are actually the last two I'm going to for major functions. The setting the volume information for setting the label. I believe I talked about that. The shutdown, we get a shutdown call when the system's ready to shut down. Okay. And then we actually have to do, we can do low-level calls to the disk driver itself underneath us saying, shut yourself down, flush your own buffers out, and give him a chance to shut down. And the last major function we have here is the write, which is just the opposite of the read for us. Okay. A little bit of history, a little bit of historical perspective so you can see where this went. When we first did the file system, it was all done using IRPs. And the IRPs had a lot of information stored in them. There was a data structure that we had to allocate. It had these specific stack locations for filling in the request, being able to pass it on back and up and down. It was a very powerful mechanism for processing and communicating requests, but it wasn't very fast. So what we did is we looked at ways of using what we would term just as callbacks, where the I/O system could directly call into the file system through one of its callbacks, and just with the parameters say, here's what, for example, here I want to read this file, here's the file object, here's the offset one I want to read, here's how much I want to read, here's the buffer I want to put it in. Do it for me. And the file system then can just process that request. And essentially that's what the fast I/O encompasses, operations like that. Okay. It's, like I said, it's a procedural interface used for performing some critical I/O work that's actually performance critical, that we want speed on. We have, the way that would actually work is that when the I/O system, when the file system registers itself, it sets up a vector of callbacks to use. And the callbacks that we allow right now for fast I/O is we can read straight away data for the user, we can write for the user, we can get and query the basic and standard information of a file. We can also do some locking and some unlocking, byte range locking and unlocking directly. Now, given that we can do fast I/O and you just register yourself and you have all these, you get these calls into yourself to do this, why do we have these and why don't we get rid of the YERPs? Well, the problem with this ones is that we may not be able to complete the request in a timely fashion for the user or without tying up that user's thread. And maybe the user's thread doesn't want to get tied up for a while because maybe they did asynchronous I/O. In which case, each one of these requests has to be able to come back and say, no, I cannot do the I/O now. You're going to have to go through the long route. You have to build up an IRP, pass it to me, and then I'll process the request that way. Okay. So the way, I believe the top, well, it's optional whether you want to support it. In the actual callbacks, you can null out the fields and we won't call you. Okay. For the file systems we did, we provided standard FSRTL fast I/O calls for the reads and the writes operations. Which is actually what I would say is we want to advocate as the way to do it. In theory, but not really too much in practice, you can roll your own fast I/O calls, but you won't have, there's so much synchronization involved and so much interplay with the cache manager, you probably want to use the ones we provide. Okay. So, actually,
if you have enabled fast I/O, then will the I/O system always attend that first, as long as you have cache?
Question is, if you enable fast I/O, will the I/O system always do that first? Yeah. If it sees it, it will try to do it. Yes. If you have the callback for it, it will call it. Giving you the parameters, and it's up to then you, for you being the file system, to decide if you want to honor that request or process that request. Okay. If I were to describe a little more, going back to what we did before, we talked a little bit before, where we talked about the FCD containing this common header up there. This ties in, sort of encompasses a lot of stuff with file system and with fast I/O. If you want to use the cache manager to cache your data, and you want memory management using its modified page router to flush out pages when it runs out of memory and stuff, you have to put in this common header that the file object will point to. What's in the common header is, it actually has a header there that identifies that it's for the type of file system it is that we use. It's just a long word for that. The first 2 bytes contain what we call a node type code. The next 2 contain the size of data structure in bytes. Okay. Also in there some flags that tells whether you can do fast I/O or not. There's a quick little Boolean flag that we use for testing stuff. And we have 3 file sizes stored in there. We have the actual file size of the file, we have its allocated size, and we have its valid data length. Okay. And it's important to keep those up to date if you want the cache manager to use them right for you. We also have 2 resources there. Resources being the executive resources that allows us to acquire exclusive or shared access to different parts of the system. David tomorrow, when he talks about synchronization, he'll actually cover those two resources and how to use them quite a bit. So I'll just mention that they're there, and that's how we essentially synchronize it. Okay. So, that's not a request. That's it. So, here's the slide I had here, and I really got to do a change on this, which is, since everyone has a copy, hopefully, if you see the word optional, better scratch it and make it mandatory. Okay. And like I was saying, this common header is used by the FastIO, and it provides synchronization, state information, and size information for us, for every string. Okay. Let me go back. Okay. So far I've talked a bit about the environment we program in, the data structures we use, and a little bit about, or I tried to give broad strokes, the operations we have to perform, and give you an idea of what's going to be coming up tomorrow, or in the next few talks, about the comments headers and how that synchronization is done. I spent a minute or so talking about this, how we post requests or handle requests in the system. I noticed Daryl mentioned the FSD and FSP paradigm that we use for it. I'll give you a little more historical perspective on that too, which was, in the first file system we did, all requests came in to this, would go through one entry point, and it would be in the context of the user's thread that we would be there. And we would call that the FSD entry point, essentially because the user went and called. It was the driver entry point. It happened to be actually the first file system we did about 5 years ago now. We were pretty lazy about it, and we decided just to post everything off to this worker thread for us to do the work on. So we would take the IRP, pass it off to this worker thread, which we call the FSP thread, which would then actually process the request, finish it, and complete the request. Okay, so that's actually before FastIO was invented, because FastIO would never work this way. The way we post, we still keep the notion of posting requests, though. You want to post a request if you do not want to block the thread that currently called you. For example, if the user has done a read and you realize that they want to do it asynchronously, and the data isn't available for you, so you can't just fill their buffer and say, I'm done, then you're going to want to post the request and return pending back to the user. And the I/O system will realize, oh, this guy's got a pending back, and he wants to continue going, so he'll return to you, return back to the user all the way back up. Okay. The way it's sort of phrased here is that if the user does not want to block the thread, the operation must be processed by a thread that can wait, which is, the way it is the system, we have this pool of worker threads called EX worker threads, all at different priorities. There's about 3 different priorities I think we have. Critical, hypercritical, and ultracritical, along those lines. Where you just simply post it to the queue, and that queue, then the thread there can process the request, can pause if it wants to, can wait, can be blocked by the request, handle the request, and be all done. It's... Okay. Is that right? Okay, that's right, yes. The last few things I want to talk about have to do with more specialized stuff in the file system. That, at least in terms of more special topics, little guides that you have to be careful of if you're going to do a true file system NT. The first one is you got to handle page faults properly. By page faults, I simply mean that you're running along and some user, or maybe even you as a file system, touched a piece of code or piece of data that's not in memory. What's going to happen is memory management is going to realize it's not there, it's going to issue a read request back to the file system to fault in the page containing the information. Okay. Like I say, this can occur with regular files. That's the whole notion of using mapped files on NT, is that you can map a file, map view of the section, and you just touch it. And if it's not there, memory management will materialize it for the user. And materialize it for the user by issuing the read request down to the file system. Like I say, it's for map streams and also for the paging file. The paging file being the ones containing all our page data structures of page pool. The big thing about page faults is that they pose very special problems for the file system regarding synchronization. What could happen is you would get a request from the I/O system, for example, to read a piece of data someplace. And you're marching around your own data structures. You touch a piece of memory like an FCD that's not in memory. All of a sudden you take a fault in the cache manager, or actually this case doesn't have the fault, but you can take a fault in the cache manager, the memory management. It's going to go way back to the file system itself to issue the read on the paging file, or issue the read to bring the data in, and you have to bring it off the disk. Well, this is all one thread working, and you have to be very careful to not deadlock when you're doing this. You have to be particularly careful not to make sure that any resource you have up here, this one doesn't try to acquire. Or, in other cases, if you have another file system or another instance of a thread doing an I/O request, getting a fault with another request, that they aren't intertwined with each other. You would have a deadlock that way. So, the biggest thing I want to just warn people is that there's a lot of issues regarding deadlocks with respect to page faults. Can I wait till after? Or, okay. You just remember it now. I'll wait till after, okay. Okay. That's not the only one. Just a single fault wouldn't be so bad. NT, we take, well, there's a single fault. NT, you can have two faults. I believe it's 3 strikes, you're out. Okay. Where we can actually be in the file system 3 times for different things. And this is just another, this is just a more complex page fault that you have to handle. An example of where this can occur is you've issued an I/O, the user's done an I/O request. The file system is trying to bring in the user's data. So it maps the user's data, touches the user's data. The cache manager says, oh, I got to bring that page in. And through memory management, the cache manager decides to bring it in. Goes back to the file system to actually do a read of the file. That read says, gee, I'm going to have to look at my retrieval information for this. And it looks up its retrieval information, and lo and behold, that retrieval information might be in paged pool. And so it takes a page fault there, which goes off to handle the fault again in the memory management, in the I/O system, going back to the file system saying, I want you to read from the paging file. And then from the paging file, you'll do your read to get the paging file back in just to read the retrieval information again. It's important that when you're processing the paging file read down here, you never take another fault, because you're not allowed to. It's sort of a catch-22. You can't bring in any more paging file because while you're trying to bring one in. So for the file system, it's important to have the code and all of its data structures for reading and writing the paging file in memory at all times. Never paged out. The last little point here is something we've always been struggling with in NT, in particular NTFS now, having to do with stack usage. The bad point of all this, it's a nice model that allows us to nest our page faults, handle them right, go back up. The problem is each takes a lot of stack of your kernel stack, which is a limited resource. And you'll find out that after 2 or 3 page faults of having yourself on the stack, if you aren't careful, you'll run out of stack. And there isn't anything that you can do about when you run out of the stack. So one thing to keep in mind when you're writing, essentially the read and the write routines that handle your page faults in this, is not to be stack hogs. Okay. Let's see. Error handling. Okay. This is sort of just the thread to give you the paradigm that we use for handling errors in the file system. The most common error you're going to have when you're writing in a file system is you go to allocate pool and it's not there, because you're going to get a false back. You call exallocate pool and you'll get a null back. Or in the case of you use the FSRTL routine, you call FSRTL allocate pool and you'll actually get a raise, because we did it that way. And I can show you, I'll explain that structure in a little while. So the most common error is you run out of memory. You run out of page pool or non-page pool. And you have to be able then to make sure you clean yourself up and you return the proper error back to the user. Okay. The other type of error you have to handle is that a lower level device driver returns an error, in which case you want to handle it back to the user. For example, you might have got a parity error doing a read, or just some other error. Okay. File system errors never occur because there's never any bugs in them. Going on. Other things the file system has to handle is that we want to be able, actually, I don't know what it's doing on this slide. The file system, you want to make sure it doesn't get suspended, terminated, or actually receive APCs while it's running. I believe it's APCs, yes. Because actually what that does is that'll just complicate the page fault example I showed you even more. And so in the file systems, when we actually run, we have an enter critical region and an exit critical region, where we stop ourselves from being suspended or having APCs delivered to us. Okay. Termination is really not a problem. We won't ever get terminated. The reason why we want to do that in particular is for example, if we get suspended for some reason or paged out and we have a resource or a lock, it'll never get freed up unless we get brought back in. And there's a lot of problems with that, so we want to get away from that. Just another issue that you want to look at whenever you do this file systems is priority inversion. Priority inversion is a problem where you would have, essentially you have two people essentially maybe reading or writing from the same file, but one person might be actually doing the processing, the other person's sort of waiting for them, where the one waiting for it is a high priority than the one doing the processing, or the one holding a resource. For example, someone might be trying to do a create file, and they're holding the resource to do a create, and it's blocking everyone else out who wants to do other operations who are actually a higher priority. I can't give you a solution for it, but I have to tell you that is a problem you always have to worry about. Okay. The way we handle it a little bit of file systems in the NT is that when you hold a resource, if you hold it for a long time, and there's someone behind you waiting for the resource, every so often the system, I guess, will wake up and give you a boost or a kick, the one holding the resource, the priority boost, to try to get around that. Okay. The next two slides, I should simply go over the file system skeleton. This is sort of the programming paradigm we use in NT. For every major IRP function code, we have an entry point that we have to put into the file system when we register ourselves. And the way we actually label it is we call it FSD entry point. We would say, for example, it would be fat FSD create, or fat FSD read, or NTFSDevCon' create or read. And the skeleton for it is you want to enter your critical region and exit your critical region on both sides of this. And we always use a try except around it. One thing we do a lot in our file systems, and we find it very useful, is to use the exception handling mechanism, structured exception handling, so that we know whenever we enter this part, if for whatever reason we bomb out, we'll exit properly. Okay. We also use a try finally a lot. For example, if this was a try finally, if you grab the resource spin lock up here, you enter your try. In your finally, you want to be able to release it. And then it doesn't matter how you exit out of that, provided there isn't a compiler bug, you release the spin lock. So everything's That is a great programming paradigm to use, and it's a great tool. Okay. In the FSD case here, we enter the file system, we call a common function that'll do all of our processing, and then we have an exception filter that'll handle all exceptions that we expect to have happen, and then we might process an exception here. The exception filter would look for stuff like if the low-level device driver, the exception filter, for example, if you access violated, you want to be able to have the exception filter probably bug check your system because you did something wrong. But other things would be, for example, if some lower-level function here raised saying, I can't wait, status, you better post this request, then down here in your process exception, you can take the IO request package you got in and post it. And that's what we do here. Can I wait till later? When we want to post a request, we post it to this FSP dispatch routine. And what the FSP does for us in our programming paradigm is it takes all the requests that get posted, enters the critical region. Actually, this doesn't have the case statement. Okay, anyway. I should draw the picture for you. This is the wrong slide. I'm sorry. This is sort of if you're looking at the CDFS or any other file system we have, this will sort of understand you the structures of how things are put together on a per module basis. Every routine we have has an FSD entry point that'll get called, like I say, as FSD by the IO system to do the processing. And we also might have, some of them would have, this is sort of a generalization, but it'll get you to understand how things work. There'll be an FSP entry point that'll get called by dispatch by the worker thread itself doing it. And each one of those would call a common routine that would process the request. So what would happen would be you enter the FSD entry point to say to do a create. You go down here to the common routine, try to do the create, and say, gee, I can't do it right now. You post the request. Later on, when the worker thread wakes up and gets it, he'll call the FSP entry point, which will go back to common routine. That's sort of the model we use. We actually have changed the model a little bit, but I show the changes, but this is sort of the general model that's used, where the worker routine, we would have this SP dispatch routine, which is a big case statement, or switch statement, if you like C, which will case on the major function code and call each of the FSP entry points. Okay, that's historically how we did it. You might find some sources that are still done that way. As an optimization, after we did this, we sort of said, gee, this is dumb to have this guy call this guy here. So we decided to get rid of him, and have him call directly. But this is the structure. If you look at any of the modules that we have, this is essentially the structure. Okay? So this stuff would be, for example, if I tell you the nomenclature, this would be in a file called create.c. It would be in a file called open.c, close.c. All of the major functions have files like that. And also in the file systems, the nomenclature is for any support routines, like for NTFS, we have a bitmap routines, some bitmap support. We always suffix it with an SUP. So we have bitmap sub.c. So all the support routines, which aren't major function codes, FSD entry points. Okay. We also have some allocation support routines and stuff like that. This one's in the FSP dispatch, FSP DISP routine module. Okay. That's basically how the things are put together structurally. Oh, you gave me a summary. I forgot about that. What I wanted to do, and hopefully I did without losing a lot of people, is in broad strokes, show you how the file system sits in the NT system, its environment, who it can call, who it can't call. I didn't give you the actual calls. You can look at the source code and find them out, and or you can ask us later. But I wanted to just give you a general feeling of where a file system lives and what environment it lives in. There's a lot of complex operations it has to perform when it does, but there's only a few places that it gets called in. There's those few major function codes it gets called using, and there's only a few operations it can perform. It's not an infinite number. It's just actually a very small set. Okay. And the last little point is that I should tell you, because we always get it all the time, is that file system performance from a user's perspective is critical. When they type a dir, if it goes line, 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 you'll hear about it quickly. Okay. So it's important to be able to turn around the user's request quickly as you go through. I believe that's all. Now I'll take some questions. I don't know where to start. You want to?
When does the file system recognize it's actually run?
Gerald? File system, they run.
What was the question?
When the file system recognizes it actually run? I wish I could remember.
Okay, how about my second question then? Maybe we can do that later.
Okay.
Can you explain what DASD-IO is? What does the acronym stand for?
Oh.
What is that?
DASD-IO. What does that mean? DASD, or how you like to say it. It's direct access, when you want to open up a volume and actually physically read and write the sector of the disk. That's what we call direct access I/O. Yes.
The one that I had wait for. You were talking about pitfalls and stuff, and scaring the heck out of us with that. So my question is basically, if you just have an FCB1 at page faults, then an FCB2 comes in later on the same page, wouldn't then the cache manager know that the FCB1 is already in the process?
Client page faults. Yes.
Okay. Good. So we don't have to handle that situation.
Yes. The question is, if you have with a client page fault, if one person touches a page and starts bringing it in, but the page isn't present yet, and another person comes in and touches the same page, memory management will handle it all for us. Okay. Memory management will wait for the next one to. We'll actually wait on knows that the operation's going on the first one. Okay. It's important for it to complete, but yeah, no.
Okay, and same thing would happen internally within the file system if you need an FCB that is on a page, and then you need an FCB that is on, that page faults, and then you need a second FCB on that same page, but
that's where you're going to the page file twice, and you can't. That actually can't happen because it's when you're processing, like an FCB will live in paged pool. Okay, it's part of the paging file. When you're processing a read or a write for the paging file, you don't take any other faults. It's just resident code, resident data. You just go straight through and take it in, bring it out. Okay. Okay, so it's not that bad as I made it out.
you determine that you are accessing the paging file for requesting the paging file?
Yes, I believe there is a bit for that. I'm almost positive. Is there a way to tell you're accessing the paging file? Is the question, and the answer is, I'm sure there is. I can't remember the actual name of the bit.
The guys in the back room are lined up out there by the door. Let's take a question from them.
Okay, someone in the back.
Any questions from the back room at all? No? Okay.
The EX critical region, that's not a spin lock, that's not a global mutex. The file system is not single threading. What is the EX intercritical region is locking out all other accessors in front end of the file system for the duration of the procedure?
No, he wants to know what the EX intercritical region is for. It's originally to make it so we don't ever get suspended, if I remember right. What it is essentially locks us out from getting NEPCs delivered. APCs being, then we can get interrupted to do something else, and we don't want to do that. I can't remember if it's suspended. David Goebel remembers for sure exactly what it was now. It's such a long time ago for me. Essentially what it is if we don't want to get ourselves out of the system, say suspended, terminated, or whatever, while we're holding some resource, because then the whole system will grind to a halt.
It's not that it's single threading all the requesters. It's not grabbing a mutex so that you're following.
No, not single threaded. No. It just, what that does is it just changes the state of the thread that's running, so it can't get interrupted. Yes.
What was the question?
Can you page fault anyway? Yes, you can get a page fault. It's your own page fault. Those are special kernel APCs. You can get special kernel APCs still. Another question?
The kernel stack limitation applied to the FSP?
Yes. Hopefully, a lot of the stack won't be gone yet. But yes, it does apply.
The same stack.
Does the FSP have a kernel stack limitation? Yes. All threads have a kernel stack limitation. You can't just assume the kernel stack on some threads is infinite. It's usually very small, in fact. 4K, 8K,
Yes, when you're in a critical region, are there any limitations on things you can or can't do? Like, can you still fire spin lock?
Yeah, you can do all that stuff. You can, if you're in a critical region, is there any limitation? There isn't any limitation. Just got to remember that when you exit the critical region.
There's no limitation on what kind of page cool, non-page cool things.
No limitation. No, not at all. Another question.
You need to lock in your read-write code to avoid the multiple page fault problem. How can you know the range of memory that is locked down?
The question is, how do you know which range of memory you want to lock so it doesn't get paged out? Say, for example, when you're processing a page fault. Okay. It's the coding paradigms we use in NT is that we can specify at the very top on a per routine basis whether it's pageable or not pageable. It's actually one of the it's not intrinsic. It's one of the defines you get up in front. Well, you essentially say pragmas, one of the pragmas. Essentially, what section you want the code to go into. So whether it's a page section or non-page section.
That would be static the entire life.
Yes. Now there is other ways where, given, I haven't used it yet, but I know the driver uses this, device drivers use this, where you can specify a routine and simply say, I want this routine page or not to ever be paged again. Okay. Or you can say you want it to be paged. Okay. For file systems in particular, I should say, and I'm going to sort of back up on that now I told you this. For a file system doing paging I/O, say to the paging file, you never want to do that. Why? Because it's really expensive. It's slow. Okay. Yes?
You don't always know if your file system may not have paging file.
So you could do this. Yeah, that's actually, you're continuing on. Once you realize, for example, you know when you're on one of the create options, one of the flags in create is you know you're creating the paging file. You know there's an open for the page file. If you want it to be tricky in your file system, you could say, well, I'm not ever going to do the paging file unless I get a create call come in. And once create call comes in, then I do these other calls where I'll lock down the routines that actually would do that. That's a good way of doing that, yes.
So what's the routine?
Anyone remember the name of the routine back there? Lou remembers it. You can ask Lou tomorrow. He's the memory manager. He'll tell you what the name of the routine is.
Maybe you should tell him that there are some outstanding questions on these things so you can be prepared.
Hopefully you'll all bring them up as well. But yeah, we'll tell them they're outstanding questions. Writing them.
Any other questions?
NT, there's some operations that you want to hide from the user, such as some type of file system, but you want to hide that.
Hide from the user. And he wants to in NT, you want to have operations that you can hide from the user, like retriable IO requests, I guess. Is that like, or if the network's just flaky or really slow, or you get a bad connection, you just keep on retrying it. That's pretty much, it's, from a file system perspective, that really isn't an issue, because we sort of expect our lower level device drivers to provide us, hopefully, a perfect medium. Okay. But as far as, like, give an example, in NT, in the file system right now, we expect our disk drivers, and we expect the device drivers down. If they get a marginal read error, or write error, we expect to retry it. And if it's really bad, then to come back and tell us it's really bad, it's a real failure. But if it's just a soft failure, we'd like it just to continue on. Okay. Did that answer the question?
Well, it answers the media point, but not the network point.
You have to ask the network guys. Yes.
Okay. Fast I/O, is that something that should only be used for so-called basic file systems? I mean, or standard old-fashioned file systems using disks rather than a network redirector? No,
network you want to use it too. Essentially, it's in fact the redirection we have in NT.
I'm thinking, because of the extra delay for the network, does it really gain you?
It actually gains quite a bit if you think about it, because if your server or whoever is caching the data, the process is reading, if the data is cached, you're going to get it fast right away.
Yes.
The whole part about fast I/O is you get the data from the cache right away.
You're right.
Removable media. How do we detect it when you take a drive out, put it from one place to the other, and move it back, and modify it and move it back again, stuff like that? I'm not the best person to answer that. You'll have the best person, by far, the best person to answer that tomorrow. David Goldman will answer it. I give you a little history. What David has done is David essentially did all of our removable media support for NT. He owns the fat file system that we don't have removable media. He'll tell you exactly what you have to do if your media gets popped out right in the middle of writing it or in the middle of reading from it, you want to create, go someplace else and gets brought back in. He'll tell you exactly what you have to do with that. He'll be the best person.
CDFS?
Read only. Doesn't matter, right? Yes.
Can file system requests be canceled while
Yes.
the IRP is queued for the FSP?
Yes. Yes, there is. Yes, I can. You can cancel the request. Cancel an IO request. Can the IO request be canceled? And when can it be canceled probably? You'll find that you can cancel the IO requests essentially when a user can issue a cancel anytime they want on an IO request while it's outstanding even. Okay. Whether the file system honors it or not is another question. Because the file system might say, oh, you're too late, I'm going to finish this request anyway. For example, if you did a create and you're halfway through the create and a cancel came in, you just say, forget the cancel. I'm all the way practically through the create. I'm done. You're out. That's it. But when it's sitting in a queue, we actually do have mechanisms so you can actually cancel. Yes, it can be. One more question. Yes.
Mr. QA guy, who's actually going to issue that cancel?
Nobody.
The cancel is issued by the 132 API.
It's not called by 132.
No, if you kill the process.
Is there a constraint? Yeah, it's an internal, right? It's an internal, right?
I think this is probably a good time to call it an end for
Okay. Well, I think
It's just not in Win32. Nobody's
to
going
ask questions.
Yeah.
I don't understood the question quite well.
What was the question again?
What was the question again?
Who we should cancel is the 3600 system or the IO system?
There's no API to issue to cancel IO from Win32, so nobody's going to do it.
I know how to do it in code mode, so you better handle it.
Yeah.
That's an answer.
From a file system standpoint, it doesn't really matter because the file system has to handle the cancel. End of story. I believe, and we should ask Daryl the question because I don't know the answer for certain. I believe it's the I/O system that issues the cancel, but I'm not 100% certain of that. Okay. So, I think we'll cut off questions there. We're running, not late enough to worry about. A little bit of administrivia. Thank you very much, Gary. Gary will be around.